So, can everybody hear me okay? I'm sure everybody here in this room knows what the baseband is, and I hope that most people in this room feel similarly to how I do, that having the baseband closed and proprietary is a really bad thing. Now, I know a lot of people have no problem whatsoever with using, say, Windows and Mac OS, even though free open source alternatives like Linux and FreeBSD have been around for ages. Some people still have no problem whatsoever with using Windows and Mac OS, even though you don't have to. But in the case of phones, in the case of the cellular baseband, the people like me and Richard Stallman, people who actually more about freedom and user empowerment, for us, having the baseband be so closed and proprietary without source code, where you don't know what's going on inside it, it's really distressing for people who are freedom lovers. And the problem is even worse for those of us who prefer the old-fashioned non-smart cell phones. And by old-fashioned non-smart cell phones, that's what I carry in my purse right now, a good old-fashioned cell phone. And the problem when you're using an old-fashioned non-smart cell phone is the baseband is the entirety of the phone. The baseband is all there is. They don't have a separate application processor. So if your baseband is proprietary, like it is in all currently existing phones, then your entire phone is proprietary. You can't, there's some bug in the UI, some button works differently from how you want it to work. If you had the source code, you could just easily fix the bug yourself, right? But if you don't have the source code, if it's all closed and proprietary, so the situation on phones today is similar to how things were with computers in the early 90s, before we had Linux and FreeBSD and all these other wonderful things, when we had were these horrible proprietary operating systems. That's the current state of affairs today on phones, which is really distressing for those of us who are all about free software and user empowerment. Now, I know most people, I'm probably one of the very few people in this room who choose to use an old-fashioned smartphone without Android, without all of those things. But even for the majority of you who do use smartphones, there's still the proprietary baseband even in the smartphones. And from what I've heard, for the past 10 years or so, about 10 years, people have been expressing concerns, smartphone users for the past 10 years or so have been expressing concerns that having the baseband be so closed and proprietary when we can already open up everything else except the damn baseband, that's kind of a bad thing. So even those of you who are not dumb phone users, those of you who do like the smartphones, hope you'll agree with me that that freeing the baseband, breaking it free from the clutches of proprietary world would be a good thing. So let's look at the prior art. Let's look at what people have done in the baseband space before me. So obviously, considering the kind of conference we are at, I assume most of you have heard about Osmocom BB. Probably a lot of you have played with it. Just out of curiosity, by a show of hands, how many people here know about the Osmocom BB? What's on the screen right now? How many people know, familiar with it? Yeah, quite a few. Now, the thing with Osmocom BB, as you can see, it works just great if all you want to do is security research. If you want to hack on GSM networks, play around with them, sniff off the air, and transmit your own on the air packets. Yeah, Osmocom BB is great for that purpose. But the problem is, what if you're a security researcher, one thing, but I'm not a security researcher. I'm a freedom fighter. I'm all about putting free software. If you want a phone as an end user, with the end user hat on, if you want a phone where the baseband is free as opposed to proprietary, for that purpose, Osmocom BB is just not going to do any good because, they don't even run the software itself on the phone. They run it on an attached PC, and everything is kind of like, the toy level. It's not really commercial product quality. And another thing is it's kind of a dead project because the things you can do with Osmocom BB today today are exactly the same things you could do with it 6.5 to about 6 years ago. It was, yeah, there was no real progress made. Now, this is not to say that the people behind SmartCom-BB, they are also the same people are behind other projects, which I'm a lot more interested in. You know, the SmartCom people also do a lot of work with cellular infrastructure, and that's a wonderful work they're doing, making open source base stations and all the infrastructure that goes behind that. So they've been busy working on that and haven't really had any time to devote to SmartCom-BB. So it's not really their fault that SmartCom-BB has been a dead project for the past 7 years. But the fact remains a fact that it is a dead project. So when I came along, I entered the scene in 2011 or so. I started looking at this, and yeah, so, you know, me coming as an outsider, you know, I was not born in the West. I don't, you know, subscribe to the values of the Western culture. The people who created SmartCom-BB, they were very, very careful about respecting all the copyrights. They were very careful about not making any directory use of the proprietary source code from TI. So, I mean, as you can see here, so they were using the knowledge from the leaked sources. So the people behind the SmartCom-BB, they readily admitted that yes, they looked at the leaked proprietary source code from TI, but they only looked at it. It was like an eyes-only thing. They looked at the source, they studied it, but they did not make directly use of it because that would be violating copyright. But again, I'm not a Westerner. I don't subscribe to those Western values, and so I figured, you know, looking at this, the problem with fresh eyes as an outsider, well, why can't we just make directly use of the TI leaked sources? I mean, people say, yeah, you know, what if you get sued? Well, I personally feel that the chances of me being sued for doing this, what I'm presenting right now, probably in terms of probability, is probably less chance than being randomly struck by lightning while walking down Oceanside Beach in California, which is where I'm from. So I'm just not afraid of being sued. That's not a concern for me. But first, I had to get access to all of the leaked docs and all of the leaked sources. And when I entered this scene back in 2011, those source leaks and those documentations, they were just all over the place. They weren't gathered in any one central place, and people were talking about them in a very hush-hush, whisper manner, which I don't like. I like things being open and public. And so this is the current URL that you see here. Of course, back in 2011, this URL did not exist. It was a different location. But that's where it lives right now. So over the past 6 years, I've been growing this collection. So every source leak, every leaked document that I could find related to TI basebands, I collected it at this place. So feel free to go to this FTP site and check out everything that's there. It's quite a big collection. So what are the actual major source leaks? So these are the three really main ones. And the first one, the TSM30 source, that's the one that most of you, or at least most of the people who have played with SmartCom-BB and so forth, are going to be familiar with. Because the TSM30 source leak came first. It was like before my time. I don't know how long ago it was. But it's been around for a long time. The TSM30 source is very complete. It's almost 100% complete source. There are very, very few parts which are in binary objects, and you don't really need those parts. So for all practical purposes, it can be considered to be 100% source. And everybody in this scene, everybody who been poking around with this kind of stuff knows about it. And as SmartCom-BB people, that's their claim. The claim which I'm about to show, that claim is actually false. But the claim that the SmartCom-BB people make is that this TSM30 source right here was the primary #1 source of knowledge for how to drive the TI Calypso chipset. Now, here's the big problem with the TSM30 source, is that the target platform, the platform that it targets, is a really oddball platform. I mean, yeah, sure, it has the Calypso chip, but the Calypso is just a digital baseband. You also got the analog baseband, you've got the RF transceiver, and all of those components are very oddball in the TSM30 version. And to make it worse, the TSM30 phones themselves are legendary unobtainium. I mean, as active as I have, I mean, I have devoted the past 6 years of my life to this project, and as even someone as deeply immersed into this subject matter as I am has not been able to get a hold of a TSM-30 phone. Those phones are extremely rare. Now, I know there are some people who have them. You know, Dieter Spar, one of the early people of SMACOMBB, apparently he has one of those phones, but he's like probably the only one or two people in the world who have them. So the phones, you know, the hardware on which you could actually run the source directly is pure unobtainium, and also there are no schematics of this hardware. So let's say if the hardware were plentifully available, you know, we could reverse engineer the hardware. You know, there have been other talks right here at this conference earlier today and yesterday, wonderful, about how you can reverse engineer a PCB. So we could have used all of those methods to clone the PCB and make them in unlimited quantity if we could get a hold of, say, you know, 10 or 20 samples. But we cannot get a hold of 10 or 20 samples. And also, there are no schematics. So let's say if there were schematics available somewhere, but no physical hardware, then we could just build our own hardware from the schematics, even if we had to do our own layout. But nope, no such luck. There is absolutely no hardware documentation I could find on the TSM-30 that would make it even remotely possible to build a new device that's similar to the TSM-30 to where we could actually run that code. So basically, the TSM-30, you got the source code, it's source code in C, you can look at it, you can adore its beauty, although the code is really ugly. Adore its beauty is, you have to put it in quotes. But you can't actually do anything with this code. There's no hardware that you could possibly run it on. So, and then we come to the next one, the TCS211 semi-source. Now that one's a lot more interesting because that one actually runs on the correct hardware. So all of those phones that, that the SMACOMBB people have been working on, this phone right here that I use as my personal phone, and then all those Motorola phones, and OpenMocha phone, and so forth that the SMACOMBB people have been working with, they all have the same chipset. They have a particular version of the Calypso chip with DSP36, they have the Yota AVB, and they have the Rita RF. That is the chipset. So when people casually say Calypso, like people who know about the SMACOMBB, they'll casually say Calypso. What they really mean is this combination. And that semi-source actually targets this exact hardware platform. The problem is it's a semi-source, meaning only half source, half objects. And the part that's half objects, well, that's where all the really interesting stuff is. Layer 1 is all binary objects. The protocol stack, all the juicy stuff is all binary objects, which is kind of a bummer, but you'll see. And then finally, we've got the Peak, the ill-fated Peak mobile email device. As the company was going down, the company was closed, and their CEO publicly leaked all of the source code that they got from the chipset vendor, which was also TI, and their chipset is low costa. So these are our starting points. So this is the one which I just talked about. So this TCS211 modem firmware semi-source. So the problem with this TCS211 modem semi-source is it has been wrongfully withheld from humanity for years. So in 2011 is when I personally entered this scene. So I was kind of a latecomer. Other people were doing this long before me. But I entered the scene in the summer of 2011. And when I started asking people if they could please let me have a copy of this semi-source, absolute, flat out no. So it was like the world's most closely guarded secret, this semi-source, and it was finally liberated in the fall of 2013 thanks to a valiant Russian comrade, and that's about all I can say on the subject. But the part which you would probably like to see is this. So during the 2 years when I was begging and pleading with the people of SMACOMBB to release this source, they were making a claim that they never used it, that they were saying that no, their justification for denying access to the TCS211 semi-source to mere mortals, their justification was that saying you don't need it. They were saying we did everything we did with SMACOMBB using only the TSM-30 source. That was their claim, and I'm about to show you right here how that claim is false. So I'm going to switch to a terminal window. Hopefully you can all see. Now, can everybody see the font? Is my font large enough? I don't think I can make it larger, but can people see what's on the screen? So this is the SMACOMBB source tree. So this is a source tree of SMACOM-BB, and there are a couple of header files here, so you can see the path here. Let's see, it's this header file, or actually no, it's this other one, dsp-api.h. This is an SMACOM-BB header file, and this header comment right here. The part which I just highlighted, the highlighted statement, in fact, I'm going to highlight even more. The part which you see on the screen that is highlighted, that statement is patently false. So the file name is correct, you know, this L1 dft.h, that is indeed the file where they took it from, but they did not take it from the TSM30. And the damning proof is right here in front of you. This code snippet, which I have just highlighted, did not exist in a TSM30 source. It does exist in a TCS211 source. Now, you already saw the FTP site URL where all the sources are, so you can just go to the FTP site and look at all those sources yourselves. You know, you don't have to take my word, but you know, I'll leave it as a homework for those of you who care about such things. You can go check it out for yourself and verify that this code in this header file exists in the TCS211 version, but does not exist in the TSM30 version. This is what's called the dynamic DSP download feature. It just, you know, TSM30 code is really ancient, from 2003. Back then, this feature hadn't even been invented. So that's, you know, just one piece of evidence. There's more. There's this line right here. Especially this part, the DSP36. The old TSM30 source only supports DSP versions up to 35. Support for DSP36 again appears in TCS211. And finally, we've got one more header file right here. I draw your attention to this preprocessor, C preprocessor symbol right here. In the older TI sources, this preprocessor symbol was just called analog, just the word analog in all caps. In the TSM30 source, it's called analog. In the MV100 source, it's called analog. But in the newer TCS211 and Locosto sources, it's called ANLG FAM, like it is here. And so having a SMACOM-BB hash defined ANLG FAM as opposed to analog, again, is pretty damning evidence of their lies. Anyway, that was for the past 4 years, this semi-source has been free. It has been liberated, so we can all rejoice now. My FreeCalypso project from 2011 until 2013, for the first 2 years, it wasn't really a technical project. It was more of a social justice project. But in the fall of 2013, the social justice project was successfully completed, and the technical project began. So the rest of the presentation, you're going to see what I've been doing for the past 4 years on the technical side of FreeCalypso. So what you're seeing here is the architecture of this firmware. So you see the Calypso chipset has an ARM core and a DSP. The DSP, you can see what it does, all low-level stuff. And then you have the code that runs on the ARM. So it's pretty straightforward. You have the layer 1, you have a protocol stack, control layers. And then on the side, you have all the supportive stuff, like any other embedded system has to have. So because there's a Nucleus plus RTOS. And by the way, we found, another Russian comrade found the source code for Nucleus plus RTOS. Nucleus plus is supposed to be proprietary, and from what I've heard, even inside TI, because I actually know some former TI engineers, and they told me that even internally within the company at TI, they did not have the source for Nucleus. But like I said, thanks to a different Russian comrade, we do have that source now. Now, back to the TCS211 firmware, these two components, layer 1 and the GSM protocol stack, those two components came in binary blobs, as well as Nucleus. The rest of it came as source. So, the AT command interpreter was all source, and we've got all this Riviera environment, BSP and drivers, that was all source. So, some of you could think, well, if these are like the two most important parts, right? Layer 1 and the GSM protocol stack. So if those two are binary blobs, what good does it do? But then we have those two other source leaks. We have the TSM30 source and we have the Lacosta source. And both of those were full C source, not semi-source. Maybe we could just, take, so my first thought was when I started this project, why don't we just take the C source for layer 1 and the protocol stack out of those other source leaks and combine them with TCS211 in order to produce a full source, fully functional firmware for the Calypso. And so this was my first attempt. My first attempt to do this was in 2014, 2015. Now, the best way to really learn the architecture of some foreign alien firmware is to reintegrate it piece by piece from the ground up. I guarantee you, you can, if you get a hold of some proprietary source code that somebody else wrote, and you just start looking at the source. Looking at the source is all fine and dandy, but you're not going to get a full, deep understanding of that source until you really get hands-on. And the most hands-on way was, like I said, was to try to reintegrate it from the bottom up. So just like, we have all these layers, right? So I started reintegrating it layer by layer by layer, starting just from the bottom layer, build it by itself, and add the next layer. And this picture that you see here, this block diagram, is very oversimplified. There are interties between layers everywhere in very, very complex ways. And like I said, when you actually start going through it and putting it together piece by piece, that's when you see the real complexity of this. So around the mid-2015 is when we finally had it kind of sort of working. We were actually able to connect to a GSM network with it and send and receive SMS, but voice calls weren't working. This was broken, and that was broken. And of course, the problem here is I was taking pieces from, it was mismatches. So I was doing mix and match and taking pieces of code from the TCS211 version and other pieces of code from the Lacosta Peak version, and they're different. There is a lot of evolutionary gap between those two sources. So they're not just going to mesh it, they're not going to connect like Legos. And then trying to, so if I had a working reference, the half source, half binary version worked just fine, but this version that we built, it was built with GCC. So this GCC built blob-free version did not work. Well, when you have a version that works and another version that doesn't work, you try to narrow the differences between the two, right? But here, the differences were just so great. There were so many variables changed at once that it was almost hopeless. So I decided to go for a different approach. Now, my eventual goal is, the goal is still the same. I want to have firmware practically usable that can run on a phone that I can carry in my purse, just like any other lady, and fully functional end-user phone, but have the firmware built from full source, no blobs, and have it built with a free compiler, GCC or one of the others. Certainly, having to use a proprietary compiler is not acceptable. But that's the end goal, But we can take some compromises on the way there. We can have some intermediate stages which are not quite. So the approach that I took, that I'm taking right now, is a more gradual, more incremental approach. So I started with a known working reference. I started with the TCS211 firmware for the Calypso, where there are these two major blocks, layer 1 and the protocol stack, the binary blobs. And instead of trying to rebuild the whole firmware from the ground up, let's just change one variable at a time. Replace one component at a time. So just try to deblob layer 1, or try to deblob the protocol stack. So the protocol stack, which is called G23M, that one is actually quite chipset independent. So I was able to just take it wholesale from the Lacosta version, which is full C source, and drop it wholesale into this hybrid environment. That has been successful. There are still some minor bugs to be shaken out, but nothing is trivial. It's definitely non-trivial because we still got evolutionary differences. Even though it's chipset independent, there is still, common header files. The so-called CDG header files had to be regenerated, and there were all these tricks which then we're not going to have time to go into here. But now layer 1, that was the interesting one. Layer 1 is very, very, very chipset dependent because its job is to drive the DSP. And the DSP is different between Calypso and Lacosta. The hardware registers are different. The RF transceiver is different. And L1 drives all of those things. And the source that you find in because Lacosta is newer than Calypso. So the Lacosta source that we have is the newest, most recent of all of the TI source leaks. And if you look at the L1 source in the Lacosta version, you will find that the code pays lip service to backward compatibility. At first glance, it looks like if you set the preprocessor the preprocessor symbols correctly, then if you set chipset to 10, you set the ANLG FAM to 2, and you set RF to 12, and you set DSP to 36. If you set up all those preprocessor symbols, then it looks like the support for the Calypso is there, but it's deceptive. The support for the Calypso is bit rotten. When TI declared Calypso to be old news, and they started working on Lacosta, they only cared about Lacosta at that point. So the code paths, the conditional compilation, the hash ifs, the code paths which are specific to Calypso have been bit rotten. So they would make changes for Lacosta. At first, it wouldn't even compile. At first, if you just try to compile it for the Calypso, like I said, you get a ton of compilation errors. And if you fix all of those, and you get runtime, brokenness. So the approach that I took was a really painstaking labor of love. So my goal was, as you can see, to reconstruct the L1 source. For the starting point, for the correct chipset, we had .obj files. Now, another important thing, whoever sanitized the TCS211 semi-source, in other words, the people who removed the C source and kept only the binary objects, they forgot to delete the header files. They forgot to delete all of the .h files. So even though all of the original .c files were gone, they're missing. The .h files are still there, and they're the original ones, and they match the known working .obj blobs. So we have that. And then we have the full source for the RON chipset. So what did I do? What I did was I would work one module at a time, so one C file at a time. I would take a single module, a single .c file from the Lacosta version, and I would drop that individual .c file into the TCS211 build environment. Now, TCS211 compiles with TI's proprietary TSM470 compiler, which is a Windows software but runs on the Wine. I don't use Windows, so I run it on the Wine. And so keeping the original TCS211 build environment with the exact original version of the compiler, with all of the hash define, with all of the -d compilation options, and with all of the include paths, and with all of the original TCS211 header files. So I only take the individual .c file from Lacosta. Everything else is TCS211. I try to compile. Of course, at first pass, compilation error. At first pass, it won't even compile because there have been all these changes within Calypso and Lacosta. So I would figure out how to get it past the compiler, get it past compilation. And the next step is to actually match the binary. And this is where I have to make an interlude. I refuse to use IDA. Because I'm not a security researcher, I am a freedom fighter. I'm about free software, making software free. And, I hold the same belief as the Free Software Foundation and so forth, that the proprietary software is a cancer on the earth. Proprietary software should not exist. Anyone who writes a program and refuses to release the source code for it deserves nothing but shame and contempt. So I don't know. I was told that the people who wrote IDA are right here in this room, but I have no idea who they look like. So if you are the author of IDA and you're standing right next to me, I won't even know them. But whoever are the people who behind IDA, I have nothing but contempt for you for not releasing the source code. All software should be free. Again, proprietary software should not exist. So I won't use IDA. And actually, I have a friend of mine, a very, very strong supporter of my project. He does have a copy of IDA, and he actually ran the firmware through IDA for me. It was his idea, not mine. And he showed me the IDA output. I was not pleased with it at all. My own custom disassembler does a much, much better job. So I wrote my own custom disassembler, which, unlike IDA, is free and open source. It's on my in my Bitbucket repository. Because TI used their the actual processor is an ARM7, it's just a plain vanilla ARM7, but TI used their own proprietary TMS470 compiler. That's just what they called it, the CL470, ASM470, LNK470 is the name of the commands, and they use COF, instead of like everybody else uses ELF for ARM, but these people use COF, and it's not the Microsoft version of COF. I know a lot of people here work on Windows, so Windows has its own, Microsoft's flavor of COF, the PE, whatever it's called. This is totally different. This has nothing in common with Microsoft's version of COF. This is TI's own version of COF, and TI also has, they have their custom compilers for all of the DSPs, but in this case it's not a DSP. In this case it's a plain old ARM7 core, but TI had their own custom version of their code composer, code generator tool for ARM, TSM470, with this weird COF ABI. So I reverse engineered their COF format, and I wrote my own disassembler that is highly custom to their format. And also the objects that we got, all these .obj files that we got from TI, they have full symbolic information. They have the equivalent of Unix, in Unix, it's on GCC, it's a -G option to get you the full symbolic information. The actual option is called something different in TI's version, but it's the equivalent of -G. So we have this very rich symbolic information in most of the objects. Now, there are some objects that only have the minimal symbolic information. And of course, my disassembler supports both modes. So if you've got an object that only has the minimal symbolic information, my custom disassembler will still do a good job on it. But if you have the full rich -G style symbolic information, then my tool makes full use of all of it. So I wrote this custom TI objd is what it's called. It's a TI specific disassembler. And so what I would do is I ran all of the original binary blobs from TI, from CS211, through my own custom disassembler. And then to reconstruct the source, what I would do is, like I already described, I would take individual C files from Lacosta. I would drop the C source from Lacosta. I would drop it into the CS211 environment, get it to pass compilation, right? But it's just compilation. So of course, the object is going to be entirely different. So what I would do then, I would take the output of of TI's compiler with my reconstructed C source, and I would pass that output through my own disassembler, and I would compare it against the original, against the disassembly of the original. And then I would massage the C source, and massage and massage and massage the C source until the compilation result matches the original object blob bit for bit. And for most of those, for most of the C modules inside L1, I succeeded in reconstructing the object bit for bit, to where the only difference between the original blob from TI versus the result of my recompilation is the timestamp within the object module. Otherwise, like all the actual code and data sections would match up bit for bit for most of the objects. Now, for some other objects, I did not get a bit for bit match. In those cases where the match was not bit for bit, I very carefully, painstakingly analyzed the logic in the disassembly and confirmed with 100% certainty that the actual logic is strictly identical. Every single logic path, strict match. So now we have recompilable C source that takes the place of what used to be a bunch of binary blobs. So that's what we did with the L1. So now, but the firmware itself, you need more than just the firmware because, well, I mean, it's kind of obvious, it's not on the slide, but it should be obvious. The other thing you need to understand the firmware. The firmware doesn't do you any good unless you can understand its workings in your sleep. And again, the only way to gain that level of understanding is to go through the effort of rebuilding it from the ground up, which is what I did in my first attempt. But then you still need all the other tooling that goes around it. So you need the tools in order to, so once you've built, okay, so you have the source code for the firmware, great. So you compile it, you get an image. How do you actually flash the image onto your phone or modem? You need the tools to do that. And then, okay, so you actually run the firmware. It crashes. How do you debug it? So you need the tools to capture the debug traces. You need to understand what kind of debug traces to put out. You need to understand how to enable, disable different debug traces. You need tools to do all of this. And also there's a file system. So the modem, the GSM modem, has its own Unix-like file system with a hierarchical directory tree. And the file system is totally custom. TI invented their own. So I had to figure out the workings of this file system and develop tools for it. So you need tools where you can take a file system image and actually see what the files are inside. You need tools to read and write those. You need a tool to create files, delete files, create directories, delete directories, rename, and so on. You need tools to do all of this. The working on TI's highly non-standard, highly custom file system. And all of those tools, those I wrote myself. So the only thing for which I got the leaked source, I got the leaked source for the firmware itself. I never got any kind of source or semi-source for the tooling. And most of the tooling only existed as Windows binaries, and even the Windows binary version. I got some of those binaries, but not all of them. So for most of the required tools, I don't even have a copy of the original Windows binary. I don't really care for it. I mean, why would you want a Windows binary when you can have a full source version instead? And it was easier for me to rewrite those tools myself from scratch than to search the world trying to find a copy of TI's original version. So another big effort in the project was, recreating all of this tooling. And then finally, we've got our own hardware. And since I've got my ESD strap on right here, there are some people who just touch exposed circuit boards without ESD protection. I mean, working as an engineer in a hardware environment, I frown on that practice. So I am wearing an ESD strap like you're supposed to. And this is the actual board. So there's a picture of it on the screen, but the physical board is right here in my hand, so you can see how small it is. It is just, it is 90 by 50 millimeters is the size of the board. So this is the actual modem. Now, if you're wondering why did we have to build our own hardware, so the people, so the chipset here, the chipset on this modem which I built is the exact same chipset is on the phones of the SmackMBB people have been hacking on. So people may wonder, okay, why did they go through the trouble of designing and building this board? Why not just use one of those dirt cheap Motorola C139 phones? I mean, you can go to eBay right now and type in Motorola C139, and you're going to see a bunch of listings for like $8 or something. Even today, that's how many of them they were made. But the problem with those crippled phones, they are crippled. Because again, my project and SmackMBB have different goals. The goal of SmackMBB was to just have a hacking tool and nothing more. So if all you want to do is, sniff and hack and do those kinds of things, using one of those dirt cheap Motorola phones is perfectly good. I mean, you're going to want to spend thousands of dollars in custom hardware when you can just buy a $20 or less phone. But my goals are different. My goal eventually, my long-term goal is to build my own phone. My eventual goal is to have a phone which I can carry in my purse like any other lady and use it with the end user hat on, but have it be 100% free and open source. And for that purpose, the existing Motorola ones are just not good enough. They're crippled. There's just too many problems. Since I knew that I wanted to build my own phone eventually, well, building your own phone is kind of a big undertaking hardware-wise, so you kind of have to approach it in baby steps. So my first little step on the journey toward building a complete phone is I built this modem. So this device that you see in front of you, this is where, I assume people can see, when I move my mouse cursor, people can see it, right? People can see what I'm pointing out. So this is the power input connector. So the chipset runs on battery power. So So here I use this power supply. So the power comes in here. Here you connect the antenna. Here you stick in a SIM card. And these are headers. So on this header, which I'm showing here, these are 2 UARTs. So this device is a modem. It's a modem. It takes AT commands. You know, the firmware takes AT commands. The hardware doesn't care. The hardware you can put whatever. The hardware itself is 100% open source. The design files for this board are public. So right now, I'm not selling these boards yet. I only have like 2 working ones. So it'll be a while before they're going to become available. But when they do become available, somebody says, hey, mychaela, your asking price for those boards is way too high. Well, you can just go to the FTP site and download the Gerber files and all other design files and see if you can build it yourself for less. If you can, great. So the hardware itself is 100% open source, and you can run whatever firmware you want, but if you run my firmware, you're going to get an AT command interface on this UART right here. Which, if we have time, I'm actually going to give you a demo of this thing working. So now, of course, the biggest problem, the biggest limitation of this solution, which I have to be honest about, is this entire solution only works with GSM 2G. Because this chipset, it is a GSM chipset. This chipset does not support UMTS, WCDMA, or LTE, or any of those things. And aside from the chipset, we only have, we have a leaked source code from TI for a commercial product quality GSM GPRS protocol stack. We do not have, at least I don't have, a copy of leaked proprietary source for a commercial quality 3G or 4G protocol stack. So, what if somebody else, wanted to do a project similar to mine, but supporting the newer technology, supporting the newer stuff? I don't know. I've heard that there are leaks floating around. Those leaks from, Qualcomm and MTK, the ones that I was able to get my own hands on, I looked at them briefly, and they look mostly like semi-source to me again. I see that all the really juicy stuff is all in linkable binary objects and libraries, and the stuff in C-source is just, the dress and the decoration around it. But those are the ones that I've seen, and I haven't given them enough time. So if somebody else succeeds in finding a complete, leaked source for some newer chipset that supports 3G, 4G, wonderful, awesome. I'm just not aware of such a thing existing. And another thing is, if somebody does find such a thing, it'll probably have to be a project for somebody else. I'm already too invested in the Calypso. I just don't see myself throwing away all of this work and restarting completely from scratch over the different chipset. And as a word of advice for anybody else, if somebody else tries to do such a project, starting using some newer chipset, if you manage to find a source leak from Qualcomm or from MTK supporting some newer 3G, 4G chipset, and the source is complete enough, it's still going to be a huge amount of work. I mean, like I said, for me, I got my hands on the source code back in 2013, fall of 2013. It is now June of 2017, so 3.5 years. It took 3.5 years of solid technical work to get this project to where it is now. So getting your hands on the leaked source is really just the beginning, so just be aware of that. And the hard to beat strengths is another thing that's really important about being able to build your own hardware like this. Is when you can build your own hardware, you have the freedom to package it in whatever form factor you like. So let's say one of you wonderful folks here, let's say one of you folks manages to liberate the baseband on some smartphone manufacturer ABC model XYZ smartphone. You find a way to liberate its baseband, and now you've got an Android smartphone with a free baseband. Great. But doing that, you cannot change the physical form factor. So if the physical form factor of your phone that you started with is a glowing slab that runs Android, no amount of software hacking will ever transform it into something other than a glowing slab. So if I want my phone to be of the traditional form factor, traditional phone with a small non-touch sensitive LCD and a traditional set of dial buttons, if I want that kind of phone, I have to build my own hardware. But in a similar vein, let's say if somebody wants to have an open source cell modem for laptops that you can plug as a USB stick into your laptop. Or let's say somebody wants an open source cellular modem that they could use as a building block for their latest, coolest IoT, whatever project. You still need to have freedom of choosing your own form factor. So that's why being able to liberate the baseband on some existing smartphone manufacturer ABC model XYZ is nowhere near as attractive as being able to build your own hardware. And of course, to build your own hardware, you have to have the chipset data sheets, you have to have reference schematics, ideally reference PCB layout, and I succeeded through painstaking years of work in gathering all these materials for TI-Calypso, but I don't know how much luck somebody else is going to have getting an equivalent for some Qualcomm or MTK. And then, okay, another question is how much do we liberate? So with my FreeCalypso solution for GSM2G, you have full control of everything, like down to the burst modulation, demodulation. The only part which is still kind of a black box is the actual burst modulator and demodulator and the voice codecs, that kind of stuff, because that stuff resides in the DSP, which runs code from a mass CROM. But everything above that, you have full control over. And even the DSP is fully subservient to the ARM. It can never do anything on its own. And the ARM controls at this exact time, I'm going to send out this type of burst. And so you have control to that level. Whereas if you were to take, there have been other people, there was one Russian hacker boasted on his blog, oh, look at me, I succeeded in freeing the baseband on my Qualcomm phone. But the only thing this guy succeeded in, he took one of those semi-sources, there was a Qualcomm source leak where it's mostly binary blobs and the C source is just addressing around it, and he was able to rebuild it from this source, which, doesn't accomplish all that much because all the juicy bits are still binary blobs. You don't have anywhere near the level of control and in-depth understanding of the protocol stack that you have with this GSM2G solution. So that's why, I've been arguing for a long time that 3G, 4G technologies should be considered immoral, having to give up, throw away all this wonderful work that has been done for GSM2G and having to restart from scratch on some newer 3G, 4G chipset, that is the approach, that is the path of weakness, that is the path of submission, that is not the path of freedom and empowerment. So we, as citizens of the world, should, every one of you should call your carrier, your cellular carrier, and tell them, we do not want 4G LTE. We want 2G forever to be able to run, to use these open source solutions. And now there are some fallbacks. Okay, so if all the carriers, like here in USA, T-Mobile is the only GSM2G carrier left. Here in Canada, it's Rogers. So, if T-Mobile USA and Rogers Canada were to shut down the GSM2G networks, what recourse do we have? Well, I did mention at the beginning that those same people who were not working on Osmocom BB, instead, they've been working on Osmocom cellular infrastructure. So these folks, there are several companies that make open source GSM base station hardware, and there are all these wonderful projects, open source, 100% free open source projects that support, all of the cellular infrastructure. So you can actually run your own GSM base station in your own GSM network using 100% open source hardware and software. And you can already do this today. Literally today, all that already exists. Of course, the problem is spectrum regulations, right? Spectrum licenses. Well, that's why I say if everything else fails, we may have to move to some third world village where we can do, have our own way. So now, what do I use in the interim? As I said, my eventual goal is, to build a phone just like this. This phone right here is a Pirelli DPL-10. That's what I'm holding in my hand. So eventually I want to build my own phone just like this, but 100% open source. But I have to use something in the interim. I have to use something in the meantime. And So and right now I run its original proprietary firmware, because on this model you've got the core chipset is the exact same as on my own board, but because there are all these undocumented peripherals, the display, the ringtone generator, and so forth, with all these undocumented peripherals, there's just no practical way to run liberated firmware on this hardware model, which is why my eventual goal is to build my own hardware. So, I already showed, what the ultimate end goal of the project is. I already talked about that. I already talked about how you can help FreeCalypso now. So that's kind of important, is even though we do not have a liberated, fully liberated GSM-2G phone yet, at least, just like I'm currently using a proprietary phone because that's all that exists, nothing better exists for the moment. Using a proprietary phone that's GSM-2G as opposed to 3G, 4G is still a morally superior solution, because when you use a GSM-2G phone, an old-fashioned phone, your carrier can see that you are using the old GSM-2G network as opposed to the newer one. And so the more people there are using GSM-2G, the more pressure we can put on the carriers to keep those networks around. So my wonderful partner sitting right there, she has a lovely Nokia phone that I don't know what baseband it has, I don't know what OS it has, but the important thing is it is a GSM-2G phone. So every time, yeah, she's waved that phone. So every time she calls me to tell me how much she loves her, that call goes through GSM 2G networks. And whether it be Rogers here in Canada during our stay or T-Mobile when we go home to California, our carrier sees that we are GSM 2G users and that we refuse to use the 4G LTE network that they market so much. And I urge every single one of you to do the same, because that is one direct material thing that every one of you can do with very little effort to help this project and to help advance the cause of a free 100% GSM baseband or any kind of cellular baseband. Because the thing is, for GSM-2G, we already have a free baseband right here. Now, I don't think I'm going to have enough time to give a demo, but you're more than welcome to catch me afterwards. So this thing works. This thing, already works today. It is 100% liberated source. And whereas for 3G and 4G, I don't know of anybody who is even trying to create an equivalent, an equivalent of what I have done, but for some newer technology for 3G or 4G. I don't know of anybody even attempting such a thing, even close. So that's why I feel it is so strong for all of us to fight for the continued preservation of GSM 2G networks. So, and that is the website. So, okay, well, I don't know if the REcon folks can tell us how are we doing on the time. Do you want to do questions? Do you want to do a hardware demo? What do people say we should do? So what? How long is the hardware demo? Maybe a few minutes? Okay, let's demonstrate the hardware. So here is the power supply. So the board which I built takes in battery emulating power. So the chipset is designed to run off of a lithium-ion battery, but here I just use a power supply to power it. And what did I just drop? Oh, it's just a hairbrush. And the board does not have native USB. The board only has serial directly on the board. And it is not RS-232. The signal that comes out of the board, the UART, it's actually just low voltage, 2.8 volt, 3.3 volt tolerant UART, or two UARTs actually. There are two UARTs. So I use this an off-the-shelf USB to UART and just an FTDI adapter with a custom cable. And let's see, so that is the IRDA UART. The IRDA UART goes to the B side of this board. And the modem UART goes to the A side of this board, right here. So that's just the FTDI adapter, that's all there is. And we connect a USB cable. So what you should see now is LS USB. So there it is. Oh, I mistyped, I'm sorry. So what you see right here, I'm going to highlight. So this modem, when you use my modem with this off-the-shelf FTDI adapter to the Linux host, it just appears as two USB serial adapters, TTY USB 0, TTY USB 1. So I'm just going to run a serial terminal on TTY USB 0. So term dev TTY USB 0 115 200, and I'm going to press the power button on it. I'm going to press the power button, and it says AT command interpreter ready. So now we have AT commands here, and we also have a debug trace. So I'm going to open another terminal window. RVinterf dev TTY, and this is one of those programs where I mentioned I wrote all the tooling, all the support tools that go around it. I write myself. So that's what you're seeing. So what you're seeing on the screen right now is the debug trace output from the firmware, and this is my own program running on the host PC. Again, 100% free open source, of course, that decodes the debug trace. So now we are going to give it some commands. There is still a hardware issue. You know, this command is just like disable sleep mode. It's just purely hardware. That needs to be resolved. I'm enabling verbose error messages, and I am going to enable cellular functionality. So this command brings up the interface to the SIM card. So the SIM card is now alive. Now I give it the command to connect to the default cellular network. So as it's working here, you can see the debug trace. So right now it's trying to acquire the frequency burst.